Okay, one more class of reactions that we want to talk about, and that would be redox reactions. So let's take a look at those. Okay, to be able to talk about oxidation reduction reactions or redox reactions, you have to be able to assign what we call oxidation numbers. And oxidation numbers are a pseudo-charge assigned according to arbitrary rules. In other words, the reason that things have an oxidation number they have is, well, because the rules say they do. You know, is it totally arbitrary? Is there no rhyme or reason? No, there's kind of a rhyme or reason to why they have the numbers they have. Basically, they're kind of like a charge, but they're not exactly the same. You know, even in covalent molecules, you can have atoms with oxidation numbers, even if it's not a charge. But if it's a ion or something like that, it usually has the same oxidation number as the charge. So it's similar to a charge, but not exactly a charge. And the reason why they have the oxidation numbers they have is because, well, the rules say they do. What it kind of comes down to. Oxidation numbers are kind of an electronic bookkeeping of sorts, I guess. Because in a redox reaction or an oxidation reduction reaction, it's all about electrons. What you're doing is you're trading electrons. This is picking up electrons, this is losing electrons. And so what you have to be able to do is you have to be able to keep track of where they are, and you have to be able to keep track of where they're going. And that's what oxidation numbers allow you to do. So if we're going to talk about all that in an even reasonably meaningful way, I guess we got to talk about oxidation numbers first. All right. So here are some rules for assigning oxidation numbers. Are they perfect? No. Will it tell you everything? No. Can you do a lot of elements and most of them that you would run into? Yes. So this will get us down the road. All right. And I won't throw anything at you that you couldn't assign from the rules. Your book has a certain set of rules there, and it's pretty much the same as what I've got. I just kind of have them here in a little more compact situation here for you to be able to assign. So let's take a look at the rules. All right, rule number one. It's the easiest rule, but everybody always forgets this rule. The oxidation number of an element in its most common state is 0. So if you see an element and it's sitting there, it's doing nothing, it's minding its own business, oxidation number is 0. So therefore, the oxidation number of iron in just iron metal, 0. Fluorine, you find as a gas, is F2. The oxidation number of each of those fluorines in F2 is 0 because that's fluorine in its most common state. All right, as I said, the easiest rule, but the one everybody always forgets for some reason. All right, rule number 2. The oxidation number of a monatomic ion, a one-atom ion, is equal to the charge of that ion. So whatever that ion is, charge-wise, that's what the oxidation number is. All right, so for example, here is an iron 2+ ion. Okay, the oxidation number of iron 2+ ion here would be +2, because that's what the charge is. If I had an iron 3+ charged ion, the oxidation number would be +3. Do you remember we were talking about how transition metals can form different oxidation states? And I said that would make more sense later on down the road. Well, here you go. This is iron in a +2 oxidation state, and this is iron in a +3 oxidation state. It just basically means that transition metals can form different types of charges. Okay? And so, yeah, that's all it really means. Here's a sulfide ion, an S2-. What's the oxidation number there? Well, it's -2. Oxidation number of monatomic ions equal to the charge of the ion. All right? Rule number 3. The oxidation number of a group 1 element in a compound, +1. Remember, group 1 elements form +1 ions. That's why it's +1. If it's just a group, if it's like sodium metal, if it's just a group 1 element, then it's 0, because that's sodium in its most common state. But if it's a sodium plus, or if it's in a compound, +1. If it's in a group 2 element in a compound, +2. Aluminum, +3. Fluorine, -1. All right, notice these are the same as the ions that they typically tend to form. Now, you'll notice I just said fluorine. I didn't say your halogens are -1. Why did I not say that? Well, because they're not always -1. There are cases where your halogens can be positively charged, not -1, typically in polyatomic ions. But basically what it kind of comes down to is if you see a halogen in a binary compound, in other words, with one other thing, particularly if it's a metal, it usually is -1. All right, but there are cases where it's not -1, like in a perchlorate, for example, where it's like +7. See, so I can't really give you a rule that says the halogens are pretty much always are always -1. They generally are, but there are cases where they're not. However, I can't think of a case where fluorine is not -1. It's just pretty much always -1. So, what I'm trying to do is I'm trying to give you rules that work, at least 85% of the time. If I gave you a rule that worked 50% of the time, you might as well just guess, because your guess would be as good as my rule. So, not everything is always 100% this or that. It's life is a complicated thing. So I try to give you rules that at least work 85 to 90% of the time. So that rule does work. Fluorine always -1. I can't think of a case where it's not. But yeah, your halogens aren't always. So they usually are, but not always. All right. The oxidation number of hydrogen in a compound is almost always +1. Why did I say almost always? Well, because it's not always. There are compounds out there called hydrides, where you have like an H- ion in them. Normally you see them with reacting with very extremely reactive group 1 or group 2 metals. You end up with metal hydrides, and it's -1 there. But really, pretty much most of the time, just about all the time, anytime you'll run into it here, probably +1. All right. The oxidation number of oxygen in a compound is usually -2. Why do I have to say usually? Well, because it's not always -2. There are a class of compounds where you have like an O2 2- ion, and those are called peroxides, like sodium peroxide, like hydrogen peroxide. Those, in that case, it's actually -1. There's another class of compound called superoxides, where you have like an O2 with a minus charge, like KO2, potassium superoxide. And it's actually, each one of those is like -1/2. But those are extremely rare and very unstable, and they tend to break down into peroxides, which are also a little bit less rare, but still very unstable. And those break down into normal oxides, where you have an O2- ion -2. So that's the most common case is where it's -2. The only time I think you would run into anything in this chapter where it's not -2 would be maybe hydrogen peroxide. They may throw H2O2 at you, but even then, I don't think they would. But you could use the fact that hydrogen's always +1, almost always +1, to figure out the oxygen from that, and we'll talk about that in a minute. But yeah, if you see oxygen in a compound, -2. Okay, but there are exceptions. There's always an exception to the rule out there somewhere. All right. Okay, well, that takes care of quite a few elements, but that doesn't really cover 90-something different elements. So do I have like 80-something different rules for you to memorize here? No. The last two rules kind of cover everything else. Okay? And so rule number 5, the sum of the oxidation numbers in a molecule equals 0. So when you add up all the oxidation numbers in a neutral molecule, it's got to add up to 0. Generally, you use this if you know everything but one of them, and then you can use that rule to figure out what the oxidation number of that element is. All right, rule number 6 is pretty much the same as rule number 5. The sum of the oxidation numbers in a polyatomic ion is equal to the charge of that ion. All right, so if you think about it, it's really kind of the same rule as rule number 5. What's the charge on a neutral molecule? It's 0, so the sum has to equal that. What's the charge on a polyatomic ion? Well, whatever that charge happens to be, so the sum has to equal that. So really, rule 5 and 6 are kind of the same rule if you want to look at it that way. All right, so how do I use this to assign oxidation numbers? Well, let's take a look. Okay, so let's start out. Here's H2SO4. Okay, in a water solution, H2SO4 would be what? That would be sulfuric acid. That is H2SO4. It's one of your 6 strong acids you're supposed to memorize from the last video, right? Okay. Can you assign oxidation numbers for every atom in that molecule? Okay, well, let's see here. Here's hydrogen. Do I have a rule for hydrogen? Hydrogen, a compound, is what? Well, it's +1. Okay. Do I have a rule for sulfur? No, I don't have a rule for sulfur. So what am I going to do about that? Well, I'm going to skip it. Okay. Do I have a rule for oxygen, a compound? Oxygen, a compound, is what? -2. Okay. So how do I get that sulfur? Well, does it make sense that if I add up the oxidation numbers of all these atoms in this molecule, it has to add up to what? It's got to add up to 0, because the sum of the oxidation numbers in a molecule add up to 0. So I've got 2 hydrogens here at +1 apiece, plus my sulfur, whatever that is, we're going to call it X for now, plus I've got 4 oxygens at -2 apiece. When I add this up, that has to add up to 0, according to rule number E, or rule 5 here. Okay? Can I solve for X here? Sure I can. 2 times 1 is 2. So 2 plus X plus, that's a -8 there. So 2 minus 8 is -6. So X minus 6 is equal to 0. So therefore X is equal to what? It's got to be equal to +6. See? We're using the fact that we know all the rest of these and not the sulfur and these 2 rules to figure out what the sulfur is. Now, what if I didn't know 2 of them in there? Well, then I'd be out of luck because I can't do that. But if I know everything but 1 of them, then that's how I figure out what the oxidation number of the other one is. And that's how you deal with the ones that don't have a rule. Want to try another one? Okay. Well, here is a Cr2O72-. What is that? It's a dichromate. It's one of your polyatomic ions you're supposed to know. Okay. Do you have a rule for chromium? No, there's no rule for chromium. Okay. Do you have a rule for oxygen in a compound or polyatomic ion? Yeah, oxygen in a compound or polyatomic ion is what? -2. Okay. So I know the oxygen's -2. What's the chromium? Well, I don't know what it is, so we're going to call it X, but I know I got 2 of them. So 2 times X plus, I've got 7 oxygens here, each at -2 apiece. When I add all this up, it has to add up to what? 0? Now it's got up to -2. Why? Because the sum of the oxidation numbers in a polyatomic ion equal the charge of the ion. So -2. So 7 times -2 is -14. 2x minus 14 is equal to -2. Add 14 to both sides there. You get 2x is equal to +12. Divide both sides by 2. X is equal to +6. So the chromium here is +6. They don't always turn out to be +6, by the way. It just happen to be that way for both these examples. But that's how you figure out the chromium. See? Okay. Now, you can write the equation out like this if you want to. But here's kind of a shortcut method, and this is the way I do it. All right. What I do is, you'll see this little scribbling up here above this little formula here. I go through and say, okay, what do I know? Well, I know oxygen is what? -2. Okay, so I'm going to put that right above the oxygen. I'm going to underline it. All right. The number on top is what all of those add up to be. Okay, so if I have 7 oxygens here, each at -2, that's a total of what? -14. Okay? So, whatever these chromiums happen to be over here, what do they have to add up to be? Well, I know the sum of these have to be -2, right? So, what -14 equals -2? Well, 12 minus 14 equals -2. So, these 2 chromiums together have to be +12. How many chromiums do I have? Well, I have 2 of them. If I have 2 of them and together they're +12, that means each one must be what? +6. So see, it's the same thing as doing it over here. You're just doing it here kind of in a shorthand method above. The oxidation number of each individual element is down here on the bottom and underlined, and there is a reason why. And what they add up to be is up here on top. If you can do it this way, great. If you can do it this way, great. But you need to get to +6 here some way or somehow. Got it? Okay. Well, why do I need to know something about oxidation numbers? Okay? Because here's what oxidation and reduction really are. Oxidation is an increase in oxidation number. If you see an element on one side of the equation, and then you go to the other side, and the oxidation number has become more positive, or you can think of it in terms of less negative, when we say increase, then that substance is being oxidized. Reduction is a decrease in oxidation number. So in other words, it's becoming less positive or more negative. You can think of it that way as well. All right, got that straight in your head? Okay, here's where we kind of twist it around a little bit. What's actually happening in a redox reaction? Do I see little +2s and -5s floating around in solution? Well, no. Oxidation numbers don't exist. They're a theoretical construct that we use to keep track of what's actually happening. What's actually happening is a trade of electrons. And this is why we call them redox reactions or oxidation reduction reactions. It turns out that they always occur in pairs. You never have oxidation without having corresponding reduction. You never see reduction without oxidation. Now, it's possible to have two things being oxidized, but something still has to be reduced. You can't have two things being oxidized and just being oxidized. Okay, always occur in pairs. Why do they always occur in pairs? Well, because oxidation is a loss of electrons. Okay? Reduction is a gain of electrons. So if something's losing electrons, well, they got to go somewhere. That's conservation of matter. So that means something's got to pick them up. If something's picking up 6 electrons, it's got to come from somewhere. So that means something else has to lose 6 electrons. Or maybe I have two things, one that's losing 3 electrons and one that's losing 3 electrons, but the total number of electrons traded has to be the same. It's just conservation of matter. And so that's why you can never have two oxidation steps occurring on their own. I can't have something losing 6 electrons and something losing 2 electrons and they just disappear. Something's got to pick them up. So in redox reactions, the total number of electrons being traded has to be the same. And that's why we call them redox or oxidation reduction reactions. Okay? So oxidation is an increase in oxidation number or a loss of electrons. Reduction is a decrease in oxidation number or a gain of electrons. Oh, we can keep that straight, can't we? Well, it gets a little difficult. So how do you keep it straight? Well, here's how I keep it straight. Oxidation is an increase in oxidation number. Reduction is a decrease in oxidation number. Does that make sense to you? That's pretty simple. Okay. So think about it. If my oxidation number is increasing, if it's becoming more positive, what must be happening to me electron-wise? I must be losing electrons. See, because remember, electrons have a negative charge. So if I'm getting rid of negative charge, I'm becoming more positively charged, right? So therefore, oxidation is a loss of electrons. If my oxidation number is decreasing, it's either becoming less positive or more negative, what must I be doing electronically? Well, I'm picking up electrons, because the electrons have a negative charge. So the more I pick up, the more negative I get. So therefore, reduction is a gain of electrons. I think of it in terms of oxidation number first, and then make the mental transition, say, okay, well, if this is true, then that means electronically this must be happening, and so on and so forth, and work my way through it. That's why I'm not memorizing 4 separate definitions that have no relationship with each other. It's easier, if you're just memorizing random things, you're going to forget it 2 weeks from now. But if you know why things work the way they do, you have a fighting chance of remembering. Got it? Okay, well, I'm going to make it even worse here. Now, sometimes when you're in the laboratory, you're interested in what's being oxidized and what's being reduced. But sometimes when you go into the laboratory, you've got a certain substance and you say, I want to oxidize this substance. What am I going to add to oxidize this substance? Well, you're going to add an oxidizing agent. An oxidizing agent causes something else to be oxidized. If I want to reduce something, I'm going to add a reducing agent. A reducing agent causes something else to be reduced. Think of it in terms of an agent, a baseball player. You got a baseball player, he's got an agent. Does that agent actually get out there and field ground balls and hit for you or anything like that? Well, no. He, negotiates with you, on behalf of you with, for contracts and, things like that. But doesn't actually play. Maybe you're going on a trip. So you go to a travel agency. And does the travel agent actually ride on the plane with you to Hawaii? No. He just kind of says, well, I can get tickets on Southwest. It's pretty cheap. There's a really good place to stay. It's a little bit off the beach, and most people don't know about this, but it's pretty cheap, so I'll get you a place there. They set it all up, and then you go, and then you pay them a certain fee to do that, right? Well, an agent does something for someone else. So an oxidizing agent causes something else to be oxidized. Okay, so here's where it gets fun. If something else is being oxidized, what's happening to the oxidizing agent? Well, it itself is being reduced, because you can never have oxidation without reduction. So your oxidizing agent is the substance that's being reduced. Your reducing agent causes something else to be reduced, so therefore it itself must be oxidized. So when I'm looking for the reducing agent, I'm looking for the substance being oxidized. All right? So oxidation, increase in oxidation number, or it's a loss of electrons. Reduction is a decrease in oxidation number, or a gain of electrons. Your oxidizing agent causes something else to be oxidized, so therefore it's reduced, so therefore it's the one that has the decrease in oxidation number or gains electrons. Your reducing agent causes something else to be reduced, therefore it itself is oxidized, so therefore it's the one that's increasing in oxidation number and losing electrons. Make sense? Work your way through it. Just mentally work your way through it a step at a time, and it will make sense. If you just memorize it as 8 separate definitions having nothing to do with each other, you'll miss it. You'll get it wrong. Knowing your luck on a test, you'll get it completely backwards. You'll miss them all. But if you understand why it is the way it is, you have a fighting chance of remembering. Okay? You want to try it? All right, let's give it a shot. Okay, so here is a reaction. I've got HCl. This would be this is hydrogen chloride as a gas. In water, I guess it would be what? Hydrochloric acid, but as a gas, it's just hydrogen chloride. This would be nitric acid in water. This is just HNO3. This is actually a liquid at room temperature if you just have straight HNO3. You can react these together. What you get is you get this NO2. This would be nitrogen dioxide. A little poisonous here. Probably don't need to be breathing that. You get a half a mole of chlorine gas here, which is definitely poisonous, so you might want to do this one in the fume hood. And you get a little bit of water for your trouble. Okay, so a couple of questions here. First question is this a redox reaction? Because not every reaction is a redox reaction. So how would I tell? Well, essentially what we're going to do is we're going to assign oxidation numbers to everything in the equation. See, that's why you got to be able to assign oxidation numbers. If you see something changing from the left-hand side to the right-hand side, it's a redox reaction. If everything still has the same oxidation number on the left-hand side and the right-hand side, it's not a redox reaction. Not every reaction is an oxidation-reduction reaction. Some are, but some aren't. Okay? So the first thing I've got to be able to do is I've got to be able to assign oxidation numbers. See, if I can't assign oxidation numbers, I'm dead in the water. Can't do anything else here. Okay? So, do I have a rule for hydrogen in a compound? Yeah, hydrogen compound's +1. So we're going to put a little +1 up here and underline it. Okay? If this hydrogen is +1, what does this chlorine over here have to be? It's got to be -1. Why does it have to be -1? Well, because the sum of the oxidation numbers in a molecule have to have 0. Rule number 5. So +1 -1 ends up being 0. Make sense? Okay? Hydrogen in a compound. +1. Do I have a rule for nitrogen? No, I don't have a rule for nitrogen, so we're going to skip it. Do I have a rule for oxygen in a compound? Yeah, I know it's -2. Okay, so that's why the -2 is sitting right here. Okay? How many oxygens do I have? Well, I have 3 of them. So if I have 3 of them at -2 apiece, that's a total of what? -6. Okay? 1 plus something minus 6 has to equal what? 0. Because the sum of the oxidation numbers in a neutral molecule have to 0. 1 plus what minus 6 equals 0? Well, 1 plus 5 minus 6 equals 0. See? And so therefore this nitrogen is plus 5. Okay? All right, right-hand side. Let's look at our products. Do I have a rule for nitrogen? No, I don't have a rule for nitrogen. Okay, do I have a rule for oxygen in the compound? Yeah, it's minus 2. Okay, how many oxygens do I have? 2 of them. At minus 2 apiece, that's a total of what? Minus 4. If my oxygens add up to minus 4, what does this nitrogen have to be? It's got to be a plus 4. You see that? Because the sum of the oxidation numbers have to add up to 0. If my oxygens are minus 4, plus 4 minus 4 equals 0. Okay? Chlorine. What are these chlorines over here? Well, they're 0. Why are they 0? Well, because that's chlorine in its free state. It's the most common state. Rule number 1. The easiest rule, the one everybody always forgets. The element in its common state is 0. There you go. Okay? Hydrogen in a compound? Plus 1. Okay? Oxygen here is what? It's minus 2 for 2 reasons. Tell me why. Well, the first rule is oxygen in a compound is usually minus 2. Okay? But both of my hydrogens here add up to be what? Plus 2? So if this is plus 2, this oxygen has to be minus 2. See, because plus 2 minus 2 equals 0. So, yeah, it's minus 2 for a couple of reasons there. All right, make sense? Okay, now, first question. Is this a redox reaction? How would I tell? Well, you remember those little elements that we underlined up here? The reason we underline the ones on the bottom is that's what we're going to look at. These oxygens here add up to be minus 4, and these oxygens add up to be minus 6, but it doesn't matter. The reason why they do that is because I have 3 of them here and only 2 of them over here. Each oxygen is still minus 2, so it's not being oxidized or reduced. Do you see anything at all that's changing here? Well, yes. Here's my nitrogen. It's changing. You know, it's going from plus 5, it's minus 4 over here. So, yeah, there is something changing here. And so, therefore, yes, this is a redox reaction. That's how you tell. Okay? All right. Well, if it's a redox reaction, that means something's got to be oxidized, something's got to be reduced, right? So tell me what's being oxidized in this equation. Well, I know that oxidation is what? It's an increase in oxidation number. Do you see anything that's over here? And when you go over here, the oxidation number is increasing. Well, look at this chlorine here. See, chlorine's minus 1 over here, and it's 0 over here. So the oxidation number of my chlorine has gone from minus 1 up to 0. That's an increase in oxidation number. It's become less negative, so therefore an increase in oxidation number. Okay? Now there's 2 ways you can say this, and 2 ways you can look at it. You can say the chlorine is being oxidized in this equation, okay, which is technically true, but the chlorine is part of the HCl. So the other way you can say it is you can say the HCl is the substance that's being oxidized. And the reason why is because the oxidation number of the chlorine is going from minus 1 up to 0. Make sense? Okay, anytime you have oxidation, that means you've also got what? You've got reduction, right? So what's being reduced here? Well, reduction is a decrease in oxidation number. Do you see anything here that's going down in oxidation number? Well, look at this nitrogen here. Here it's plus 5. What is it over here? It's plus 4. So my oxidation number has decreased. So therefore, the HNO3 here is being reduced because the nitrogen in the HO3 is going from plus 5 down to plus 4, and reduction is a decrease in oxidation number. And that's how you tell. Make sense? Okay. What's the oxidizing agent here? Well, the oxidizing agent causes something else to be oxidized, so therefore it itself is reduced. So I look and see what's being reduced here, and that would be the HNO3. So the HNO3 is my oxidizing agent because it's causing my HCl to be oxidized. Make sense? Agent does something for someone else. That's kind of how you keep it straight. What's my reducing agent here? Well, my reducing agent is the substance that is causing something else to be reduced, which would be my HNO3, which is being reduced. So therefore, my HCl is causing my HNO3 to be reduced. So therefore, it's the reducing agent. Okay, notice the HCl itself is what? It's being oxidized. Okay? So your reducing agent is oxidized, your oxidizing agent is reduced. Normally that would not make sense unless you thought it through and you understand actually what's going on. But yeah, just whatever's being reduced, that's your oxidizing agent. Whatever's being oxidized, that would be your reducing agent. And that's how you tell. Make sense? Can you do it? If I gave you an equation, could you tell me if it was a redox reaction? And could you tell me what's being oxidized and reduced? And then could you pick out the oxidizing and reducing agent? Got to know how to assign oxidation and oxidation numbers to be able to do that. So yeah, you need to kind of work on that. And no, I will not give you those rules. That you're on your own on that. I guess, you know, if I gave you the periodic table and let you write anything on it, I guess you could write that down if you wanted to. But yeah, that's you're probably on your own on that one. Okay, a lot of stuff in 4, a lot of stuff to remember. It's just yeah, it's a bit of a challenge, but you know that's why you took the class. It's a bit of a challenge, right? Everybody loves a challenge. Okay, questions at this point? I guess even if you had them, I couldn't hear them, could I? Okay, well, last thing here in this particular section is balancing redox equations. Balancing redox equations can be a little tricky. You know, I once had a professor, he gave us a list of equations to balance, just like I kind of gave you. Oh, this was in graduate school, actually. Only these equations had coefficients like 513 and 1024, you know, and 772. And so, yeah, it was a little bit more challenging than the 35 that I gave you. So how were we able to do that? Well, it turns out they were actually doable. And it was a little tedious, but it actually was not as hard as you would think. When you balance redox equations, you tend to get really big coefficients. And the reason why is because normally you're just trying to get the same number of atoms and type on both sides. But when you balance a redox equation, you have to get the same number of atoms and types at both sides. But you also have to make sure that your charges are the same, add up to be the same on both sides. And you also have to make sure the number of electrons being traded is exactly the same. If I have something picking up 6 electrons, something has to lose 6 electrons. So I have to find a set of coefficients that satisfies all 3 of those requirements instead of just trying to get the same number of atoms. And that means fairly large coefficients sometimes. There actually is a little 6-step method for balancing redox equations, which is actually in this chapter. I am not going to hold you responsible for that in this chapter. When we get to the electrochemistry chapter, we'll talk about balancing redox equations by what we call the half equation method, and then we'll move on from there. But I think it's a little bit much for chapter 4. When you get there, by the way, whether I am your teacher at that point or not, you will thank me. You will sit down and you will write a nice little thank you note to me saying, man, thank you, Mr. Anderson, for not making me do balancing redox equations back in chapter 4, because it would have just been so much I probably would have given up. You saved my career by doing that. So, you know, I'll be waiting for your thank you note on that one, and we'll move on from there. But that's pretty much the 3 types of reactions that you might run into out there. There are others, but that's a pretty good list of them, I suppose. You're probably waiting for the math, and of course that's coming in the next video. We're going to talk about stoichiometry. In other words, okay, now that we know something about grams and moles and chemical reactions, you know, how can I predict how much stuff I'm going to be able to make, you know, starting with this, making that, and so on and so forth. So, yeah, more factor label stuff coming back, and more math, unfortunately. But that should be actually the last video. So you're almost done with chapter 4, so hang in there. So I guess we'll quit there for now. So we'll see you in the next video. Bye.